we're going to start with the infinity types. So I want to look at the integral from 1 to infinity of 1 over x dx. So what I'm saying is I want to know how much area is under the curve y equals 1 over x between 1 and infinity. Or I should say, I guess, to the right of 1 is in more, because you're not really between infinity. So I might just keep destroying pens left and right here. So, right, we've got 1, 2, 3. Right, and we've got this function that's doing this kind of deal. Oh, I don't know what I'm doing. So, right, we know this point here is 1, 1. And this point here is 2, 1/2, and so on. And we're trying to figure out how much area might be under here. And even though it looks like it might be a finite amount, right? It looks like it's getting relatively small. It's actually not what's going to happen here. So we can see that, right, as x goes to infinity, 1 over x is closer and closer to 0, which is not really necessary for this, but I should mention it. So let's try and figure out how to integrate this. So whenever you're integrating an improper integral, there's going to be, it's always going to be a definite integral, first of all. Improper integrals are always definite integrals. And there's always going to be one limit of integration or somewhere between limits of integration that's problematic, where we can't really plug in infinity, right? I can't just say, I mean, people do, but it's not really appropriate. You can't just antidifferentiate this and be like, it's whatever at infinity minus whatever 1. What you're supposed to do is for any infinity or other problematic point, replace it with some letter. People, I think your book usually uses T. I often use B for an upper limit and A for a lower limit. Whatever you want. You can use Z. Just don't use X, right? Because X is already spoken for. So we can say, I'm going to find the integral from 1 to B of 1 over x dx. But then I'm going to take the limit as B approaches infinity. So that's always the idea, especially if you got an infinity. Replace the infinity with some convenient letter, and then take the limit as that letter goes to infinity. So now we're just going to treat this integral as normal, and we're going to do the limit part at the very end. So let's see what happens. If the limit is b goes to infinity, the integral of 1 over x is the natural log of the absolute value of x from 1 to b. We're going to plug in b and 1. So we're going to get, let's see, the limit as b goes to infinity. Since b is positive and 1 is positive, I can drop the absolute values. I get the natural log of b minus the natural log of 1. The natural log of 1 is 0. And as b goes to infinity, the natural log of b also goes to infinity. Right? We've seen the logarithmic graph before. It looks like this. It gets bigger and bigger and bigger and bigger as we go out to the right. So what does that mean? Well, it means that this definite integral has an infinite amount of area. Okay, so what do we say when that happens? We say that the integral from 1 to infinity of 1 over x dx, we say that it diverges. If your integral has an infinite amount of area, it is said to be divergent, or that it diverges. Yeah. On the other hand, if we have an integral that actually gets close to a particular number, we're going to say it converges to that number. Also, this language of diverging and converging is definitely going to resurface in 21C when we talk about series. So you should try to kind of really take this to heart. This does come back. So let's look at the second kind of classic example, which is the integral from 1 to infinity of 1 over x squared. And 1 over x squared is a little bit smaller than 1 over x, right? If you try graphing it, right? If I was graphing 1 over x, right, you get 1, 1, 2, 1/2, etc. I'm going to try and graph this in a way so that I can draw stuff later. But there's y equals 1 over x. 1 over x squared, well, you still get the point 1, 1. But then you get the point 2, 1, 4. And you get the point 3, 1, 9. So it gets smaller way faster. So we're asking how much area is under this curve as we go up to infinity. And I want to remind you guys, there was an infinite amount of area under 1 over x from 1 to infinity. So we're going to do the same process, right? We're going to say, okay, this is going to equal the limit as b goes to infinity of the integral from 1 to b. We could rewrite this if we want to as as x to the negative second. You don't have to, right? You can integrate however you want, but I'm going to do it that way. So still got the limit. Integral of x to the negative second is x to the negative first over negative 1 from 1 to b. I am going to rewrite this. I'm going to write this as the limit b goes to infinity. I'm going to rewrite this as 1 over negative 1 times x, or negative 1 over x from 1 to b. Now I'm going to plug in my top and plug in my bottom. So let's see what I get. I get a limit as b goes to infinity of negative 1 over b minus negative 1 over 1. And now, as b goes to infinity, this part's going to go away, right? 1 divided by infinity is super small. Minus 1 is going to equal positive 1. So we could either say that this integral is equal to 1, or if we want to use more words, we could say that the integral from 1 to infinity of 1 over x squared dx converges to 1. So if the improper integral ends up being a nice normal value, we say that the integral converges to that value. Yeah. And most of the time people will just say the integral is equal to 1 because that's kind of the convention. So that's kind of the big picture stuff, right? If the integral is infinity or negative infinity, we say it's divergent. If it's a real number like 1 or 2 or pi or the square root of 7, then we say it converges to that number, or the integral is just equal to that. And that's kind of all there is to it, really. And now, I mean, we still have to be able to integrate stuff, but that's kind of it. I should point out, because this does become a thing, basically, if the power of x in the denominator is anything larger than 1, we get that the thing is convergent. So there is something called, it's actually called the p-test, and it's the and I know it's a terrible name, right? The p-test. And there's a p-test for integrals, and there's a p-test for series that you'll learn in, which is probably when you'll actually get introduced to that terminology. But the p-test says the integral from 1 to infinity of 1 over x to the p, that's why it's called the p-test. This is divergent if p is less than or equal to 1, and it's convergent if p is bigger than 1. Even if p is just a tiny bit bigger than 1, right? If you did like the integral from 1 to infinity of 1 over x to like 1.03, and that's not getting small very fast. But if we do it, well, it's the limit as b goes to infinity of the integral from 1 to b. I'm going to write this as x to the negative 1.03. Integrate that, so I add 1 to the power. x to the, let's see, negative 1.03 plus 1 is negative 0.03. I divide by my new power, and then I go from 1 to b. Okay, I'm going to rewrite this so that this can come down to the denominator and have a positive power. So it's going to be the limit as b goes to infinity of negative 1 over 0.03 times x to the 0.03 from 1 to b. And then the limit as b goes to infinity of negative 1 over 0.03b to the 0.03 minus negative 1 over 0.03 times 1 to the 0.03. Now check this out. B is going to infinity. Infinity to a positive power, even if it's a really small positive power, is still going to get infinitely large. So infinity to the 0.03 is going to be infinity, and this whole thing is going to be 0. So my answer is going to be minus minus, so it's going to be plus 1 divided by 0.03, right? Because 1 to any power is 1. So 1 over 0.03, which I would probably write as 1 over 300ths or 100 over 3. So that's what this integral converges to 100 over 3. And let me just point out what's happening here. As long as this power is a little bit bigger than 1, then when you rewrite it this way, it's a little bit more negative than negative 1. And then when you add 1 to it, it's still just a tiny bit negative, right? Since this power was a little bit more than 1, we end up with something in the denominator that's still a little bit positive. And that's kind of the crux of why this converges. On the other hand, right, if our power had been a little bit less than 1, like, let me just switch it up real quick here. Let's say the power was 0.99. And so then this was x to the negative 0.99. And then when I added 1 to the power, I got x to the positive 0.01 and positive 0.01. Well, now look what's happening. Instead of having 1 over x to a positive power, I really have x to the 0.01 divided by 0.01. And when x goes to, or when I plug in the, when I plug in the upper limit b, and then b goes to infinity, infinity to a positive power goes to infinity. And since it's in the numerator, it's going to stay as infinite. So that's why when the power is less than or equal to 1, like 0.99, the whole thing diverges. Where if the power is greater than 1, the whole thing converges. Cool. Okay, let's do some more examples. Got lots more. Should we do? Yeah, let's. So sometimes things are worse. Worse, yeah, let's do that one. So let's say we wanted to find the integral from negative infinity to infinity of x cubed times e to the x to the 4th. All right, so fun times. When you have an infinity and a negative infinity, you have to break it up. You cannot, it is incorrect to say that this is the limit as b goes to infinity of the integral from negative b to b of x cubed e to the x to the 4th dx. And there's actually a problem in some textbook where they give you an example and they're like, if you calculate it this way, you actually get a different thing than if you calculate it the right way. So just be aware, if you've got plus or minus infinity, you can't just say it's minus b to b and b is going to infinity. Instead, you have to break this up as the integral from negative infinity to any point in between infinity and negative infinity. Usually we pick 0, although you could pick 1 or 3 or negative 2, right? Whatever you like. If something seems like it looks like it might be specifically convenient, pick that. But if you don't have a good idea, pick 0. Plus the integral from 0 to infinity of x cubed e to the x to the 4th dx. Okay, So what's the integral of x cubed e to the x to the fourth? Well, I had to do a u sub. So I wouldn't carry all of this with me while I do the u sub. I'm just going to do the u sub real quick. I'm going to say, all right, I know that u should be x to the fourth. My du is 4x cubed dx. So 1/4 du is x cubed dx. And I can rewrite my integral just like the indefinite integral. X cubed dx becomes my 1/4 du. And e to the x to the fourth becomes my e to the u. So this ends up just being 1/4 e to the u, which is 1/4 e to the x to the fourth. So the antiderivative of x cubed e to the x to the fourth is 1/4 e to the x to the fourth. And I definitely recommend, in general, if you've got some complicated definite integral, or the definite integral, where you're going to have to do a u sub or integration by parts or whatever, I really, really, really recommend doing the actual anti-differentiation just for the indefinite integral, so you can just deal with that kind of more easily. So now, here's how we're going to write this. So this I should write as a limit. Right? It's going to be the limit. I'm just thinking, fine. I suppose I should write. So this is going to be the limit as a goes to minus infinity of the integral from a to 0 of x cubed e to the x to the fourth dx, plus the limit as b goes to infinity of x cubed, integral 0 to b x cubed e to the x to the fourth dx. Fun times. Now, typically when I'm doing one of these problems, I then do each of these separately, because if one of them diverges, you're done. The whole thing diverges. If one of them converges, you have to do the other one. So usually when I look at something like this, I'm trying to pick a thing that's going to diverge. Oh, which this one totally is, because I accidentally did the wrong problem. That's all right. It's fine if it diverges. So let's see here. So looking at just this part here, I'm going to get, and I really kind of ran out of room. So let's look at that part there. So that part there, well, I know how to integrate this. It's 1/4 e to the x to the fourth. So this is going to be the limit as b goes to infinity of 1/4 e to the x to the fourth from 0 to b, which is equal to the limit as b goes to infinity of 1/4 e to the b to the fourth minus 1/4 e to the 0. And as b goes to infinity, b to the fourth goes to infinity, e to the infinity goes to infinity. So you get infinity minus 1/4, which is infinity. So this is definitely divergent. So we didn't even have to do this other half, although it would have also diverged. I wouldn't say anything about whether this diverged to infinity or negative infinity, unless I was specifically asked to. Usually you're not asked to. Usually you're just asked, does it converge or does it diverge? Let's look at another example. So let's go to one of my favorite examples. Sure. That could be good. Let's look at, again, the integral from negative infinity to infinity of, what kind of terrible thing can I come up with here? Let's do 2x over 1 plus x to the fourth dx. And now, before we start thinking about how to anti-differentiate this, let's just write out this stuff. So again, we're going to have to break this up. Let's break it up at 0, right? I don't see any good reason not to. So I'm going to write this as, so instead of writing, like the integral from negative infinity to 0 of the thing, plus the integral from 0 to infinity of the thing, let's jump straight to writing it as the limit as a goes to minus infinity of the integral of a to 0 of 2x over 1 plus x to the fourth. Okay, I'm going to ask you guys in a minute what my u substitution should be. So I want you guys to think about what's the u sub going to be for this. Plus the integral from, plus the limit. Each of the pieces get a limit. So the limit as b goes to infinity of the integral from 0 to b of 2x over 1 plus x to the fourth dx. All right. You guys have any guesses about my u substitution? I tried to make it a little bit easy to see with the 2x right there. X squared is exactly what I want. So if u is x squared, du is 2x dx, which I've totally got. And then the 1 plus x to the fourth becomes 1 plus x squared squared. So my integral of 2x dx over 1 plus x squared squared becomes the integral of 1 du over 1 plus u squared. And we know the antiderivative of 1 over 1 plus u squared is the arctangent of u, which is going to be the arctangent of x squared. All right, so that's what each of these is going to equal. So let's do this one first. So this one's going to equal the limit as b goes to infinity. We antidifferentiate this. It's the arctangent of x squared from 0 to b, which is going to be the limit as b goes to infinity of arctangent of b squared minus the arctangent of 0 squared, which is 0. All right, what's the arctangent of 0? Or let me ask you this differently. What's the angle that if we took tangent of it, we would get 0? It's 0. Okay, here's the harder question. What's the arctangent of b squared as b goes to infinity? Or what is the angle that if you take tangent of the angle, it's going to get infinitely large? Any guesses? How do I say this the right way? So you can either think about the graph of tangent. In fact, let me just show you guys. So yeah, let's Desmos it up for a second. Give me the graphing calculator. Okay, so here's tangent. And I'm also going to give it away. Why not? So if we look here, right, if we look at this blue line here, which is x equals pi over 2, you can see that as the angles get closer to pi over 2, the values get larger and larger and larger. So for the inverse function, as the inputs get larger and larger and larger, the values should get closer and closer to pi over 2. Or we can more easily see this by just, in fact, graphing the inverse function. Come on. Let's go. So there's my inverse function, and you'll notice that the arctangent function, so just like tangent has a vertical asymptote at x equals pi over 2, the inverse tangent has a horizontal asymptote at y equals pi over 2. Right? Just like that. We get closer and closer and closer and closer and closer. So the answer to the question I was asking is that as the input gets infinitely large, the arctangent of that input gets closer and closer to pi over 2. So this half of the integral converges, and it converges to pi over 2. Okay, so now we have to look at the other half. All right, so I'm going to do the limit as a goes to minus infinity. Instead of writing arctangent of x squared from a to 0, I could just plug in 0 first and a second and say it's the arctangent of, I guess I could write x squared from a to 0. But really what I want to do is just plug in 0 and then subtract and plug in a. So I'm going to write arctangent of 0 squared minus arctangent of a squared. Okay, arctangent of 0 is 0. And as a goes to minus infinity, a squared goes to positive infinity. And the arctangent of something that's infinitely large, again, is going to be pi over 2. So this is going to be 0 minus pi over 2, which is negative pi over 2. So my total answer is that this thing converges, and it converges to 0. It's kind of disappointing. I'm like, 0, all that work for nothing. But, I mean, not really for nothing, but to get an answer 0. But the reason this is 0 actually is because of something we already know. It's because we got odd functions, right? 2x over 1 plus x to the 4th is an odd function. It looks kind of like this. So 2x over 1 plus x to the 4th, how does it point at 0? If you plug in 1, you get 2 over 2, which is 1. And then it gets, and if you plug in 2, you get 4 over something large. So, and then if you plug in negative 1, you get negative 1. So it kind of looks like this. And you can see, hopefully, that the area over here is positive and finite. It's going to cancel out with the area over here, which is the same amount but negative. So that's why we get 0. I want to point out, and this is kind of an important thing. So it is true that this integral is equal to 0. But this integral, sorry, I forgot the limits of integration. This integral is not going to be 0. The reason this integral is not going to be 0 is because it's divergent. The right side is going to have an infinite amount of positive area. The left side is going to have an infinite amount, but it's going to be negative area. And since they're both infinite, we can't say they cancel out, right? We don't know that infinity minus infinity is necessarily equal to 0. It's an indeterminate form. So if you try doing this one, by, ooh, gosh, sorry, my leg just got like, all right, so, sorry, yeah, it was real exciting there. Right, this looks kind of like this. We're saying all this positive infinite area, and all this negative infinite area over here. We don't get to say they cancel out because they diverge. And so this is kind of an example of, if I write this as the integral from negative infinity to 0 x cubed dx plus 0 from 0 to infinity x cubed dx. If I look at just this one for a second, that one's going to equal the limit as b goes to infinity of the integral from 0 to b of x cubed dx, which is going to be the limit as b goes to infinity of x to the 4th over 4 from 0 to b. And then I'm going to get the limit. Gosh, these are always like so many steps. As b goes to infinity of b to the 4th over 4 minus 0 to the 4th over 4. And then as b goes to infinity, b to the 4th also goes to infinity, so we get infinity. And then we're done. Part of it was divergent, the whole thing's divergent. We don't get to say anything else. So this integral is divergent. This integral converges to 0. Okay. You guys have any questions about stuff I've said so far? So let's look at another. So I should say this is the first category of improper integral, where one or both of your limits of integration are infinite. But the other type is where one of your limits of integration, or maybe somewhere in between limits of integration, is undefined. Typically undefined in a division by zero sort of way. So I'll remind you guys just for a second, there are three main ways, or three types of functions that are kind of undefined in our world. They're when you divide by zero somehow, when you take a square root of a negative, or when you take a logarithm of a zero or negative. Square roots of negatives aren't really going to come. So for example, this integral here that I'm going to write down is trash. If I said the integral from, I don't know, 0 to 5 of the square root of 1 minus x, this is a dumb question. This is not a real question because this is only defined between, right, from, well, on this interval, right, the square root of 1 minus x, when x is 0, you get 1. When x is 1, you get 0. Kind of looks like that. And then from 1 to 5 there's nothing there. It's undefined. So no one's going to ask you a question where a whole bunch of your interval is undefined. They're going to ask you where a point's undefined. So like someone could ask you something like the integral from 0 to 1 of the natural log of x. Because natural log of x is defined everywhere on this interval except at the end, which is 0. Or someone could ask you something like the integral from negative 1 to 2 of 1 over x. Because this function is defined everywhere on the interval except at one point in between 0. So what I'm trying to say with all the words ever spoken is that these improper integrals can only be defined at like one spot or two spots. It can't be defined at like every value of x from 1 to 5. That just isn't going to fly. So let's look at this question. So when you're dealing with definite integrals from now on, you really should be thinking about, is the function I am integrating undefined anywhere in my interval? And this is kind of the worst case where it's undefined somewhere in between. So we have to break it up in between where it's undefined. This is undefined at 0. So I have to write this is the integral from negative 1 to 0 of 1 over x plus the integral from 1 to 2 of 1 over x. Sorry, 0 to 2, apologies. And then just like before, we're going to try and see if either one of them diverges. Or really what we're going to do is we're going to do one of them, and if it diverges, we're going to do the other one. Yeah. So let's do this one. So I'm going to do, let's see. So the integral from 0 to 2 of 1 over x dx is equal to the limit is a approaches 0. I have more to say about this. From a to 2 of 1 over x dx. Now, we actually should be more specific. If I'm between 0 and 2, in fact, let me draw it on the number line. There's 0, there's 2. I'm between them. Are we approaching 0 from the right side or from the left side? Well, which side of 0 are we on? Are we on the right side of 0 or are we on the left side of 0? Yeah, we're on the right side. And so you should write, and you will see, hopefully your teachers write, that really this is the limit as a approaches 0 from the right side of 0. Of this interval over x. It usually doesn't matter that much, but it is a detail most teachers will look for. So then we're going to integrate. This is not too terrible. So limit as a goes to 0 from the right. The integral of 1 over x is the natural log of the absolute value of x from a to 2. And then we get let's see, the limit as a approaches 0 from the right of the natural log of 2 minus the natural log of a. Notice that I dropped the absolute values, but because both 2 and a are positive. I know 2 is positive, it's 2. I know a is positive because a is approaching 0 from the right side of 0. It doesn't really matter, but now, what happens is a approaches 0 from the right? Well, the natural log of a, as we approach 0, the natural log of a goes down to negative infinity. So this is going to be natural log of 2 plus infinity, which is infinitely large. And we're done. This part diverged, so the whole thing diverges. Right? So we got that this part diverged. We don't know if this part diverged or converged. We don't care. It doesn't matter. Once you know that one part diverges, the whole thing diverges. So don't do more work than you have to do. Right? If you have to break an integral up into multiple pieces, you definitely want to stop once you have one piece diverging. Yeah. So let's look. I know I had another example on the board there. Which was on? Yeah, sure. So I am kind of interested to ask this question. What's the integral from 0 to 1 of the natural log of x? Okay, well, we need to, so first of all, natural log of x is undefined at 0. So we need to rewrite this as the limit as a approaches 0 from the right of the integral from a to 1 of the natural log of x. This is actually going to turn out to be a somewhat complicated problem. Okay, does anybody remember what the integral of natural log of x is? I can just dance all day. Just a little dance. It's okay if you don't. I mean, I don't always remember what it is. So to integrate natural log of x, you have to use integration by parts. So let's do that off on the side here. So we're going to let u equal natural log of x. dv is the rest. du is 1 over x dx. v is x. You end up getting uv minus the integral of v du, which is x times 1 over x dx. But x times 1 over x is just 1. So I get x natural log of x minus the integral of 1. And the integral of 1 is just x. Okay, so here's what we get. We get the limit as a goes to 0 from the right of x natural log of x minus x from a to 1. Okay, so I'm going to plug in 1. The limit as a goes to 0. We get 1 times natural log of 1 minus 1 minus a times natural log of a minus a. Uh-oh. So this is going to be 0. So I'm going to have the limit as a goes to 0 from the right of, I don't know, so negative 1 minus a natural log of a minus a. Okay, now here's the question. This part's negative 1, this part's clearly 0. What about this part? Well, shoot, it's an indeterminate form. It's 0 times a negative infinity. And to find that limit, we actually need to use Lupita's rule. So let's find some magical board space that's just going to, I guess I can erase, right? Let's do it over here. Makes me think of I'm trying to think of a other good question. Anyway, so to find the limit of that, the limit as a goes to 0 from the right of a natural log of a I'm going to rewrite this as the limit is a goes to 0 from the right of natural log of a over 1 over a, or a to the minus first. Okay, let's use L'Hopital's rule. Differentiate the top and the bottom. So the limit is a goes to 0 from the right. Derivative natural log of a is 1 over a. Derivative a to the negative first is negative 1 times a to the negative second. Bringing that back up to the top, it becomes a squared, and 1 over a times a squared is just a. So I get a divided by negative 1, or negative a. If the limit is a goes to 0 of negative a, which is just 0. So this ends up converging, which actually I wasn't expecting, to be perfectly honest. Yeah, that's surprising to me, I will fully admit. But anyway, I get negative 1 minus 0 minus 0, which is negative 1. So this converges to negative 1? Well, yeah, because, right, we're actually under the x-axis. And the part that we have found is, so here's your natural log function. And we just found that all this area here, that area is negative 1 because it's under the x-axis, but it's got an absolute value of positive 1, which is kind of neat. I will admit really freely here, I was expecting divergence because I just made the question up. Because most of the time, when you integrate a thing that has a vertical asymptote, you often still end up getting division by 0 after you integrate. You didn't here. It's kind of neat. So yeah, that's pretty cool. I learned something today. All right, let's look at some more examples. Right. So I want to be perfectly clear here, right? You might incorrectly think you could just say it's 0 times something and you get 0. And in this particular example, the answer is 0. But that's not what's correct. The reason we have to use L'Hopital's rule here is because this is an indeterminate form. And it's an indeterminate form that is a 0 times a negative infinity. Let me show you another example just to really kind of make sure you believe me. Not that you don't believe me, but like, let me prove it to you. Let me show you. So what about this limit? The limit as x goes to, 0, no, not 0. 0, yeah. Limit as x goes to infinity of x squared times sine of 1 over x squared. This part's going to infinity. This part's going to 0. So again, I have an infinity times a 0. This one's not going to be 0, right? So I want to point out, right? I don't really technically have infinity times 0. What I really have is very, very large thing times thing very, very close to 0. It's not actually 0 because I never actually get sine of 0. I get sine of a very small number, which is very, very close to 0. Just like here, I don't really have 0 times negative infinity. I have number very, very close to 0 times very, very negatively large number. And in this case, the 0 is more potent. It takes more control. It overpowers the infinity, and your product ends up being 0. It's not going to happen here. In this case, the infinity is going to kind of win out. Well, actually, no, it's not really. No one's going to win here. They're going to kind of actually find a balance. So let me show you what I mean. Stop talking. This is going to equal, let me grab different pens. Pens start to fade. This is going to equal the limit as x goes to infinity of, I'm going to write this as sine of 1 over x squared over 1 over x squared. So that I can have something I can use L'Hopital's rule on. Right now I have a 0 over 0. Top's going to 0, bottom's going to 0. And then we use L'Hopital's rule. So this is going to be the limit as x goes to infinity. The derivative sine of some stuff is cosine of the stuff times the derivative of the stuff. I'm going to cheat here a little bit. And then on the bottom, the derivative is just the derivative of the stuff. So derivative of that. Now, normally you should find the derivatives, but I noticed that the derivative of this and the derivative of this are the same, so they're just going to cancel out. These derivatives are both negative 2 over x cubed. This is negative 2 over x cubed, this is negative 2 over x cubed, so they totally cancel. And then as x goes to infinity, 1 over infinity goes to 0, and cosine of 0 is equal to 1. So in this case, infinity times 0 became 1. So that's why I had to use L'Hopital's rule there, because I had a form that requires it. When you have an indeterminate form, like a 0 times some sort of infinity, you have to use L'Hopital's rule. Good. I know it's been a while since you guys have used L'Hopital's rule probably, but they do come up in some of these. Oh, actually, yeah, they do actually come up in these relatively frequently. Let's do another one. Now, that's an infinity one, though. It's kind of off of the infinity ones. Maybe I'll come back and do an infinity one in a minute. So let's see here. Let's look at a couple more examples here. Let's look at the integral from 0 to pi of sine of x over 1 plus cosine of x. Normally, I might not be very careful here, but now I'm in the mindset of, oh, I'm looking at improper integrals. I should probably double check to make sure that the denominator is never 0. But it is 0. It's 0 when cosine is negative 1, which is when x is pi. So I have to rewrite this as the limit as b approaches pi of the integral from 0 to b of sine of x over 1 plus cosine of x. And technically, are we approaching b from the left or from the right? Is b approaching pi from the left or from the right? Are we less than pi or are we greater than pi? So what's what I'm looking for? The short way to do it, the fast way to do it, the trick is if it's the upper one, you're always approaching it from the left. If it's the lower one, you're always approaching it from the right. Because if we're between 0 and pi, we are less than pi, which means we're left of pi. If we're between 0 and 1, and we're approaching 0, we have to be approaching 0 from the right, because we are between 0 and 1, we're bigger than 0. We are right of 0. So if it's lower, you're approaching it from the right because you're approaching it from above. And if it's upper, you're approaching it from the left because you're approaching it from below. Okay, hopefully that makes some sense. So let's integrate this. So hopefully you can see that if you let u equal 1 plus cosine, your du is negative sine. So this integral, if u is 1 plus cosine of x, my du is negative sine of x dx. So negative du is positive sine of x dx. So this becomes negative du over u. And we know how to integrate that. It's going to be negative natural log of the absolute value of u, which is negative natural log of 1 plus cosine x. So this is going to equal the limit as b approaches pi from the left of negative natural log of the absolute value of 1 plus cosine of x from 0 to b. Okay, let's see what happens. Usually if you've got a logarithm, it means you're probably going to be diverging. I should say, yeah, except for the previous one, right? Usually if you've got a logarithm by itself, it often means you're going to be diverging if you're plugging in something that's going to make it 0. I should kind of take that back though, because there's at least 3 counterexamples I can think of where logarithm ones converge. So, grain of salt. So let's plug in b. The limit is b approaches pi from the left of negative natural log of 1 plus cosine of b minus negative, so plus natural log of 1 plus cosine of 0. Okay, let's see what happens when we plug in b. Well, first, I guess right here, this is just going to be natural log of 2. But here, b is approaching pi from the left. Cosine of pi is negative 1. 1 plus negative 1 is 0. And natural log of 0, that's where the logarithm has the vertical asymptote. Natural log of 0 goes down to negative infinity. So this is going to be a negative infinity plus natural log of 2, which means it's going to diverge. It's kind of hard to write. If I try to write on the board, while I look at myself writing on the board, it kind of works, but right, that's not great. Anyway, yeah, that's a good problem. Let me see. I know there's a couple more that I want to do. Yeah, not you. Oh no, not you for sure. Okay, yeah, I've got. Yeah, let me see. Sorry, I had one and then Sure. Let's look at. Yeah, I got a couple more. How much time have I got? Okay, I got 25 minutes. All right, I got time for all the things. Let me have you guys start working on this one while I do something on the other side of the board. So I want you to try to see if this one, the integral from 1 to e of 1 over x square root of natural log of x dx converges or diverges. And now if someone says converges or diverges and you don't see an obvious place where it's undefined, you should look for it. So what makes this undefined? Well, what makes the denominator 0 here? It's undefined at x equal to 1. Because natural log of 1 is 0. Square root of 0 is 0. All right. So I want you guys to write this like this. The limit is a approaches 1 from the right of the integral from a to e of 1 over x square root of natural log of x dx. And then over here, I'm even going to tell you what the u sub is. The u sub is going to be, what do you think makes a good choice for a u sub here? I mean, there's kind of an obvious thing that's stuck inside something else. Right. Because it's stuck and because its derivative is 1 over x. All right, I'm going to let you guys finish this one off while I work something out on the back side of the board real quick here. So it's going to be upside down. Oh well, such is life. All right, I figured out what I want. Great. Hopefully you guys are making lots of great headway on this problem. Cool. So let's see what you get. So I think it converges, but let's see. So I'm going to integrate, instead of integrating 1 over x root natural log of x dx, my 1 over x dx becomes du, and my square root of natural log of x becomes the square root of u. So this is going to be the integral of u to the negative 1/2 du, which is going to be u to the 1/2 over 1/2, which is just 2 square roots of u, or 2 square roots of natural log of x. Okay, so this is going to end up being, let's see, the limit is a approaches 1 from the right of that 2 square root natural log of x from a to e. When we plug in, we get the limit is a approaches 1 from the right of 2 square roots of natural log of e minus 2 square roots of natural log of a. And then we finally evaluate the limit. We say, oh, a goes to 1. Natural log of 1 is 0. So we end up with 2 times the square root of 1, which is just 2. This one converges to 2. Yeah. Yeah, we'll choose this one. Okay. So ignore that. Don't ignore that. So I want to find the integral from, let's say, 1 to infinity. We're back on the infinities again. 5 over 2x plus 1 times x plus 3 dx. And first and foremost, of course, we're going to write this as the limit as b goes to infinity of the integral from 1 to b of 5 over 2x plus 1 times x plus 3. And what do you think we might have to do to integrate that thing? Everyone's first favorite, second favorite, third favorite method of integration, where the denominator factors. That's right. You know it. Partial fractions. So I'm going to say 5 over 2x plus 1 times x plus 3 is a over 2x plus 1 plus b over x plus 3. So multiplying both sides by the denominator, I get 5 on the left. I get a times x plus 3. I get b times 2x plus 1. Okay. So what's a convenient value of x I could pick to make one of those things 0? Thank you. Someone else should write the other one while I do this. So I plug in negative 3, and I get 5 equal to a times 0 plus b times negative 6 plus 1, which is negative 5. So I get b equal to negative 1. Okay, what's the other value that's going to make this part 0? Yes, thank you. It's a fraction. It's x equal to negative 1/2. So plugging that in there, I get 0. Plugging that in here, I get 5 equal to a times negative 1/2 plus 3. Negative 1/2 plus 6 halves is 5 halves. So I get 5 equal to 5 halves a. And multiplying with both sides by 2/5, I get a equal to 2. Or just write a equals 2 because 5 halves times 2 is 5. Okay, so that means that we are trying to find the limit as b goes to infinity of the integral from 1 to b of 2 over 2x plus 1 minus 1 over x plus 3. Okay, that looks not so terrible at the moment. So let's integrate. So let's see. So I know these both look like logarithm things. In fact, I'm fairly certain, actually I'm completely certain, that the integral of 1 over x plus 3 is the natural log of the absolute value of x plus 3. I probably don't need the absolute value since x is going, maybe, yeah, leave them up there. Now, this one's going to be slightly trickier. I've got a 2. So you might think it's 2 natural log of the absolute value of 2x plus 1. Let me ask you guys, is this right? Not quite. So take the derivative of this, I get 1 over 2x plus 1 times another 2. I don't need that other 2, so I really actually don't need this coefficient here. Because the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. From 1 to b. Okay, so now we are going to, I'm going to erase some of this over here. This is where things get a little bit dicey. So if I plug in b, look what happens. I get the limit, as b goes to infinity, of the natural log of the absolute value of 2b plus 1 minus the natural log of b plus 3, minus, if I plug in 1, I get the natural log of 3 minus the natural log of 4. Okay, and this is where it's easy to get caught up. What would you want to say that natural log of 2b plus 1 is going to as b goes to infinity? Anybody? I know it takes a while to like type out the letters to spell the word that you want to write the answer for. Yes, that's right. The answer is infinity. However, this integral is not divergent. So the problem here is actually much like before, we have an indeterminate form. We have an infinity minus an infinity. And now here's the thing. If you broke up, if you were doing those, if you were doing one of the improper integral problems where you broke it up into 2 integrals and one integral was infinity and one integral was minus infinity, you would just say it diverged because you would only have looked at one half of it instead of diverged. But here, it's not that we have 2 different integrals, it's that we have 2 different pieces. And so to evaluate this limit, we actually do have to do some work. Now, fortunately, we don't really have to use Lupita's rule here. You could if you wanted to, actually, but I'm not going to. To be able to use Lupita's rule, you have to have a fraction. But I can put these logarithms together. The natural log of 2b plus 1 minus the natural log of b plus 3 is the natural log of 2b plus 1 divided by b plus 3. So this is equal to the limit, as b goes to infinity, of the natural log of 2b plus 1 over b plus 3. Minus, this is going to be the natural log of 3/4. All right. Can anybody tell me what the limit as b goes to infinity is of 2b plus 1 over b plus 3? It only takes one keystroke to tell me the answer. Now, I know you guys know the answer. You might just not know you know. So let me ask you a different question real quick. What's the limit as x goes to infinity of 3x squared plus 5x plus 1 over 8x squared plus 7x plus 2? Can anybody tell me that limit? I know you guys can. It's a rational function. The degree on top and the degree on the bottom are the same. This limit is 3/8. And there's a rule. You can either use L'Hopital's rule here, right? You can take the derivative of the top twice, the derivative of the bottom twice, and get eventually 6 over 16, which is 3 over 8. Or you can use the rule that when you have a rational function, the degree on the top and the degree on the bottom are the same. The limit is the quotient of those leading coefficients. Well, that's what's happening here. The rational function, degree on top and the degree on the bottom is the same. It's 1. And so the limit, like Mindy wrote, is in fact 2. Right? You get something, right? This whole thing is going to 2. And so the whole thing is going to be natural log of 2 minus the natural log of 3/4. And then you can put that together as one natural log and be the natural log of like 8/3 or something weird like that. Maybe the natural log of 2 divided by 3/4, which is 2 times 4/3. That one's a little crazy. A little. Okay, let's do 1 or 2 more. In fact, actually, let's do 2 side by side. Talk about how they are different. Let's do the integral from. Let's do 1 to 5 of 1 over x minus 1 cubed versus the integral from 1 to 5 of 1 over the square root of x minus 1. Okay, both of these are problematic at 1. Let's do this one first. This is going to equal the limit as b goes to 1 from the right of the integral from b to 5. And I'm going to rewrite this as x minus 1 to the negative third, just to make it slightly easier to anti-differentiate. So this is going to be the limit as b goes to 1 from the right. When I anti-differentiate this, I get x minus 1 to the minus 2 divided by minus 2 from b to 5. And now I would rather write this so that this thing has a positive power. Because to me, so here's the problem I see happening for myself. If I plug in 1 for x, or b for x, and then 1 for b, 1 minus 1 is 0, and 0 to a negative power isn't immediately obvious that, oh, that's undefined. But if I rewrite it as the limit as b goes to 1 from the right, and I write this as negative 1 over 2 times x minus 1 squared, it's a little more clear to me what's going to be happening. This is going to be the limit as b goes to 1 from the right of negative 1 over 2 times 5 minus 1, which is 4 squared, minus negative 1 over 2 times b minus 1 squared. And now we can all see that if I plug in 1 for b, b minus 1 is going to be 0, and dividing by 0 is going to be undefined. So this is going to be divergent. And, well, let me do this other problem, and then I'll talk about the intuition here. So this is going to be the same sort of process. Right? It's going to be the limit as b approaches 1 from the right of the integral from 1 to b to 5 of x minus 1 to the negative 1/2 dx. I'm going to anti-differentiate that. I'm going to get x minus 1 to the positive 1/2. Dividing by 1/2 is the same as multiplying by 2 from b to 5. I'm sorry, my plus sign looks real lame there. Okay, so I'm going to plug in 5, I'm going to plug in b, and let's write the 1/2 power as a square root, or not. It doesn't really matter. So limit as b goes to 1 from the right, 2 times 5 minus 1 to the 1/2, minus 2 times b minus 1 to the 1/2. And now when I let b approach 1, I get 1 minus 1, which is 0, but I get 0 to a positive power, which is just 0. So this one converges to 2 times 4 to the 1/2, which is 2 times 2, which is 4. But the intuition I kind of want you to see here is that if you have an improper integral where you're dividing by 0, which is a lot of the time, if you're dividing by something that's raised to a high enough power, then when you integrate it, you're still dividing by 0, it's going to diverge, right? So I can see, oh, I've got something over x minus 1 to the third. When I anti-differentiate it, I'm going to end up getting something over x minus 1 squared. I'm still going to be dividing by 0. Whereas if you're dividing by like a square root or a cube root or a fourth root or some power of a thing that is less than 1, when you anti-differentiate it, that power gets to be 1 larger, so it then becomes greater than 0, right? If this was the 1/3 power instead, right? If instead this was the cube root, and this was x minus 1 to the negative 1/3, when I anti-differentiate that, I would be getting x minus 1 to the positive 2/3. times some number out in front here. But the point is that if this power here is between 0 and 1, when you anti-differentiate, it becomes bigger than 0. And so then the 0 that you were dividing by becomes a 0 that you're no longer dividing by. Whereas here, if your power is bigger than 1, like 3, when you anti-differentiate it, the power only gets 1 smaller, or I should say it gets 1 less negative, right? Because really when you anti-differentiate it, the power does get bigger. So the negative 3 power gets bigger, but it's still negative, so we're still in the denominator. Let's see, what else? Oh, yeah, I got one last example for you guys. So my one last example is, the integral from 0 to infinity of x e to the negative x. Is that what I really want? Let's make it x squared. Let's make it real fun times. Okay, so clearly the infinity is the problem here. So we're going to make this the limit as b goes to infinity of the integral from 0 to b of x squared e to the negative x dx. You do not have to write that you approach infinity from the left. You're always approaching infinity from the left. You can't approach infinity from the bigger than infinity side. That's just not a thing. So don't worry about the left or the right for the infinities. Now for this integral here, let's use the tabular method. My u is going to be x squared. My dv is going to be e to the negative x. And then my derivatives go here, all the way down to 0. And then for e to the negative x and e to the x, the antiderivatives and the derivatives are the same, but it is the antiderivatives for your dv. The antiderivative e to the negative x is e to the negative x divided by negative 1, which is the same as multiplied by negative 1. And then the antiderivative of that is positive e to the negative x. And the antiderivative of that is negative e to the negative x. Okay, so then we do the thing, right? It is plus this times this minus this times this plus this times this. Well, that was certainly easier than it could have been. So this is going to be the limit as b goes to infinity of negative x squared e to the negative x minus 2x e to the negative x minus 2 e to the negative x from 0 to b. Okay, so I'm going to rewrite this so that these e to the negative x's are actually in the denominator as e to the x's. So now if I plug in b, I get the limit as b goes to infinity of, I guess I could write this as one fraction if I really want to. It's not usually done that way, but we could. I'm not going to yet. We got minus b squared over e to the b minus 2b over e to the b minus 2 over e to the b. Minus, now I plug in 0, and I get 0 minus 0 minus 2. All right, so let me ask you guys, as b goes to infinity, what happens to 2 over e to the b? Where does it go to? Well, the denominator is getting really, really, really big, so the whole fraction is getting very, 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 very small. Okay, but now this one's an infinity over infinity type, and so is this one. So even though most teachers, I don't know about most, some teachers are cool with you just saying that this limit's 0 because the bottom gets bigger faster than the top, technically what you should really do for this one and for this one is use Lupita's rule. So what I was actually thinking we might do is rewrite it like this. You can totally rewrite the whole thing as limit as b goes to infinity of negative b squared minus 2b minus 2 all over e to the b plus 2. And then you can use L'Hopital. So then, right, so we put the 2 out in front. And then you can use L'Hopital's rule on this part twice. So this is going to be 2 plus the limit as b goes to infinity of the derivative of the top is negative 2b minus 2 over the derivative of the bottom is e to the b. And then we get 2 plus the limit as b goes to infinity. The derivative of the top is negative 2. The derivative of the bottom is e to the b. Oh, look, that's 0. So our final answer is 2. So this integral converges to 2. But a lot of times with these e to the x times something or e to the negative x times something, often to actually figure out whether or not it converges, you're technically required to use L'Hopital's rule to evaluate those limits. So just be aware of that if you see that kind of thing happening. Just like the a times the natural log of a1 that we did, we had to use L'Hopital's rule there. The same thing is true here. You have to use L'Hopital's rule.